This is the 16th lecture of the course MTH 204A for section B. In the last lecture, towards the end we were talking about classification of groups of order PQ when P and Q are distinct primes with P less than Q. So there we have seen that if P does not divide Q minus 1, then after isolation there is exactly one group, namely the Z modulo PQZ. When P divides Q minus 1, then we do have a non-abelian group of order PQ. So in fact what we have seen is every group of order PQ must be the semidirect product of its Sylow subgroups, where the Sylow subgroup corresponding to the bigger prime is normal. Now as we were quite inquisitive there, that the way we constructed a non-abelian group using semidirect product is just by choosing an automorphism of order P from odd k, where k is the Sylow Q subgroup of G. So the question was, can different choice of those automorphisms will lead us to different non-isomorphic groups of non-isomorphic groups of order PQ. So the following theorem shows that that does not happen. So what we are going to prove is the general theorem for semidirect product of isomorphism of semidirect products. In fact, this is an exercise in the book of Damit-Foot. So here we consider H and K are two groups, where we further assume K is cyclic, H is arbitrary, and of course we have two homomorphisms, phi 1 and phi 2 from K to odd H. Both are homomorphisms. Assume that phi 1 K, that is image of K under phi 1 and phi 2 are conjugate. So that is, for some sigma one has sigma belonging to odd H. Okay. If K is infinite, assume further that both are injective. If K is finite, you do not even need that assumption. If K is infinite, assume further that these are injective, 1 1. So then the theorem says the semidirect products will be isomorphic. Okay. So if this shows that if the K is cyclic and the images are conjugate, and of course another assumption when K is infinite, then though this could be different, however the semidirect products will be isomorphic. Okay. So before getting into the proof of this is slightly technical. Before getting into the proof, let me immediately deduce the following corollary. That is, if it happens that phi 1 k equal to phi 2 k, then so phi 1 and phi 2 they might be different, but if their images phi 1 k equal to phi 2 k, their images are same, then also by this theorem we will have the semidirect products isomorphic. More generally, slightly more generally, if both of them are, phi 1 and phi 2, both of them are equal to some Sylow P subgroup for P dividing order of G, even then we will have the semidirect products isomorphic, because once both of them are some Sylow P subgroups, then they will be conjugate to each other. Okay. If both of them are Sylow P subgroups for some prime P dividing the order of this group, if both of them are Sylow P subgroup of odd H, even then we must have this the semidirect products must be isomorphic. All right. So, and as an immediate corollary, we can also see that if K is isomorphic to Z modulo QZ, sorry, if H is isomorphic to Z modulo QZ, then ought H is in fact isomorphic to Z modulo Q minus 1 Z. Okay, that's an easy exercise. So, since this is a cyclic group, for any P since it's a cyclic group, so there is a unique subgroup of order P of this cyclic group, right. Therefore, so unique subgroup of order P there exists, unique order P of ought H, okay. And from that it is quite clear that Z modulo QZ, semidirect product Z modulo PZ are same up to isomorphism, for every non-trivial phi. Because if phi is non-trivial, then the image of this group under phi will be a subgroup of order P of the odd Z QZ, and odd Z QZ is a unique subgroup of order P. Okay. So, this in particular shows that this concludes that if G is equal to order P cube, when P and Q are distinct primes, then either G is cyclic or there is a, after isomorphism, there is a unique non-abelian group, or G is isomorphic to so G is isomorphic to the, so this phi is yeah, so for some and equivalently all non-trivial phi. Okay. So, hence there are for any two primes P and Q, if P does not divide Q minus 1, then the only possible structure is this. If P divides Q minus 1, then of course in one case we can have this, and the other case we can have a non-abelian structure. So, this classifies completely all groups of order PQ. So, either it will be cyclic in the case P does not divide Q minus 1, or it will, or there will be one cyclic group and another non-abelian group. Okay. Yeah. So, now let me get into the proof of the theorem. The proof of the theorem, as I said, is slightly technical. So, you have to bear with me, several small things will happen. So, try to understand first that phi 1 x is a generator of image of phi 1, right. Similarly, phi 2 x is also a generator of image of phi 2, and they are conjugate to each other. So, it is quite clear that sigma phi 1 x sigma inverse. So, phi 1 x is a generator of phi 1 k, and once we conjugate that by sigma, it has to be a generator of phi 2 k. On the other hand, we have a generator phi 2 x. So, this will be some power of that, okay, because this is a generator of phi 2 k, this also turns out to be a generator of phi 2 k. Once that is the case, then we can immediately see for every integer n raising both the sides to the power n, we can immediately see that phi sigma phi 1 x sigma 2 x to the power n, and here we can of course switch yes, so here we can do this switch that shows that. So this shows in particular for every small k belonging to capital K, sigma phi 1 small k sigma inverse is sigma 2 k. This is quite clear. All right. Now let me write down the map which we will show that ultimately that is going to be the required isomorphism. So what is going to be? So consider the following map. So our ultimate job is to show these two groups isomorphic. Okay. So what's the how do we define that map? Simply sending each h comma k to sigma h comma k to the power a is that a. Okay. We now want to show that this map is an isomorphism. Well, so showing this is an homomorphism, I am leaving it to you. A routine verification, show that this is an homomorphism, show that this is an homomorphism. That is actually quite, it will be clear in view of this. This is a homomorphism. Okay. We now try to show this is an isomorphism. So homomorphism, the checking of homomorphism is a routine verification, a direct computation, you just do it. So how do I show that this is an isomorphism? We will try to get its inverse, because here the groups might be infinite, so counting argument may not help. So in order to find out its inverse, we will divide that into two cases. So first case would be, when k is infinite. So in fact it happens to be easier to deal with the case when k is infinite, and that in turn gives us the motivation how to proceed when k is finite. So assume k is infinite. So in that case we claim that, in fact the claim is also quite clear. We claim that there exists B in Z such that the same thing phi 2 k sigma is phi 1 to the power k for every k in k. So the argument is exactly similar to what we have done here, because we start with phi 2x. So sigma inverse phi 2x sigma will be a generator of sigma 1k, hence it will be some power of sigma 1x, call that power to be b, and then exactly this similar kind of argument. Okay. Now from this it is easy to see that, let me do it over there, or maybe I can do it here. So now next what we can see from here is so phi 2 k to the power ab. So a is the previous a. So by my choice, sigma phi 1 k sigma inverse to whole to the power b and since conjugation is there, I can push B inside. Okay, I can push B inside, and next we see that this is again same as sigma here. Yeah, so this is again same as sigma to k, right? Sigma to k, yeah. So that follows from here that this means phi 2 of k to the power ab is sigma, sorry, I am very sorry. So this will be simply phi 2 of k. Now in this case we have further assumed sigma phi 2 is injective, therefore k to the power ab is k, and once this is there, the following map it can be easily seen to be an inverse of the psi. Okay. First is the map psi. Let me define this chi. Chi is defined in this way. How is that defined? H comma k maps to sigma inverse h and k to the power b. Okay. You can immediately check if you compose sigma, this psi and chi, the way they are defined, you will arrive at identity. So clearly the psi inverse chi is inverse of psi. Okay. So thus we have dealt with the situation when k is infinite. Now let us come to the case when k is finite. So case 2, k is finite. Case 2, k is finite. In fact, let us assume m to be the cardinality of okay, so k is, here we assume k is finite. So therefore phi 2k and phi 1k both will be finite since they are conjugate, so their cardinalities will be same. Okay, let us call that to be m. Okay, so here as I said, and maybe I can also write that let me also define n. Okay, so how do we see so what would be the strategy to prove this? We would like to construct a similar map in this case as well. For that we need to have a b. How is that b constructed? Be constructed in this way. Okay. So this analysis, this argument also valid in this situation. So the only where we need k, I mean we have actually used k to be infinite is like the only way we have used the fact that k is infinite is here, when and because in that case phi 2 was injective, otherwise till before that everything was perfectly same. So up to this point same thing holds for this situation only. So here also we can think of, so like as I said, our plan is to have a b, choose a b such that here x to the power ab becomes x, right, where x is the generator of k. This in principle implies that k to the power ab will be k. So this is how we would like to go ahead, but since in this case phi 2 is not assumed to be injective, we cannot say that. The only thing that we can say here is ab, the only thing we can say here is x to the power ab minus 1 is in the kernel of phi 2, right. So we can so when k is finite, then so, and if we, as I said, if we proceed like earlier, we cannot go beyond this point, and from here we can at most claim this is to be this. but this is not going to give us anything, because we need, as I said, something very stronger, right? And well, this is same as saying x to the power ab minus 1 is identity, and can one assure that? It can be assured if ab happens to be 1 modulo n. Okay. So, this cannot happen unless this happens. Okay. This cannot happen unless this happens, or in fact these are equivalent. So, these are equivalent. So, what we want is same as, so again let me repeat. So, you want to choose a B for which this happens. So, that means the choice of B will be such that for the previous A, AB will be congruent to 1 modulo n. Okay. So, thus the strategy is that, but here when we started B, at that point of time we did not know that where AB is congruent to 1 modulo n or not. So, here we will try to choose a B such that this happens. Now, again observe that how can this happen? How come this happen if A is not co-prime to n? So, what I mean by this is, this cannot happen unless A is co-prime to n, right? Try to again follow the proof. Our plan was to find a B such that this happens. We could have proceeded as we have done earlier, but there I got stuck up to I got stuck at this stage only. I cannot go beyond that, because I do not have the help that phi 2 is injective. So, proceeding like this is not actually going to be of much help to me, because I can only go up to this, where I need this, and this is what is this means one must have this, and this cannot happen unless GCD of A n is 1. But do we have that even? Do we even have that? Actually no. So, what do we have? We have only that GCD of A and M is 1. Why so? Because you see that phi 2 x to the power A is phi 1 sigma phi 1 x sigma inverse. Okay. So, phi 1 x is a generator of phi 1 k. Once we conjugate that by sigma, it will be a generator of phi 2 k, and this is also a generator of phi 2 k, this phi 2 x. So, therefore, phi 1 x and this quantity. So, phi 2 x and this quantity both are generators of the same group phi 2 k, and that group has order m. So, therefore, only we can assure GCD of A and M will be 1, because unless you raise it to some co-prime power of the generator, you are not going to get any generator of a cyclic group. So, only we have up to this much, but we need this. So, we need to do some more work. That is exactly done in the following lemma, and in view of the lemma the proof will be over. So, what does the lemma say? The lemma says that simply says the following, that I mean, this is a general lemma. So, let A, M, n are integers, and in fact we can take n to be a natural number, and GCD of A and M is 1, and of course we do have M divides n, that has to be there, because M is the order of the image, that has to be the divisor of the order of k, which is n. So, and of course M divides n. Given this situation, then there exists A dash, an integer in Z having these two properties, which is A dash congruent to A modulo n, and furthermore GCD of A dash n is 1. Okay. Before we get into the proof of this lemma, let me show you how this lemma, how we can finish the proof of the theorem in view of this lemma. That is simple. From this A, using this lemma, we will produce an A prime. Since A prime and A are both are modulo n, they are same. So both are same in modulo m. So therefore, this is same as A prime. There is no problem will going to happen. And for this A prime, since this is congruent to 1 modulo n, so by Bezo's theorem, we can have an B such that modulo n, for that B, so you can modulo n, and once that is there, now in this case we will simply replace A by A prime and take B to be this B, then just by composing that we will see both the compositions will be identity. Okay. So what I will do is the following, using this lemma we will get an A prime. So since they are modulo m, they are same, this is not going to be hampered, the rest will also go as follows. So thus instead of psi, we will change in the definition of psi, A will replace A by A prime, and we are not going to get anything else here, because A and A prime, their difference is divisible by m. Okay. So like once this is there, we will change this by this, and for this A prime, whatever we will pick, we will define psi accordingly, that now the compositions will be identity. Okay. So before, again let me repeat how do we prove that. As I said that here our plan would be choose a B like this, because when k was infinite, we see that this, when k is infinite, we see that this map becomes a inverse of psi. So it's very curious to know whether this works when k is finite or not. But the problem was there, if I choose B according to the previous strategy, when k was infinite, then we will stuck only up to this stage, but that is not enough for us. We rather need this, and this cannot happen unless A is congruent to 1 modulo, A is coprime to n, but that is not always guaranteed, for which we need to do this. Okay. So the proof of the lemma is quite simple. So A and A prime, the A prime that we are going to look for, it must be of the following form, right, for some positive integer L, or for some integer L, it must be of this form, right, this A prime must be of this form. Now just to make, so we have to choose L appropriately so that the GCD becomes 1. So what you do is take to the product of all prime divisors of product of all prime divisors of n which does not divide A. Okay. So for that L, if you consider this, then the rest is an obvious thing, because in that case the GCD, if the GCD is greater than 1, then there will be a prime factor of the GCD. So let P be such a prime factor. Now there are two cases, either P divides A or P does not divide A. If P divides A, then in this term P divides this part, and P cannot be in the product lying in L, and also P cannot divide M, because A and M have GCD 1. So therefore P cannot divide this quantity. On the other case, that is, if it does not divide A, then this term is not divisible by P, however this term becomes divisible by P. So that is a immediate elementary verification, hence I am leaving that to you. So that proves this lemma, and in view of this lemma we prove the theorem. So again let me repeat that when k is finite, the way we should work is, we have this lemma, in view of this lemma we replace A by A prime that is not going to harm us anyway. And then we simply in psi change we take this A prime, and for this A prime whatever B we have we define chi like this, then yeah, then there will not be any problem after that. Anyway, so thus we have done a lot. So thus we this general theorem, not only it yields the classification of groups of order p cube. In fact, we will keep on using this theorem later on to classify other groups which necessarily come as semidirect products. Okay, so now let's move on. So let's now talk about. So okay, we get, as I say, we get back to applications of. I mean, we are talking about applications of Sylows. So now let's talk about groups of order 30. So what are the divisors of 30? So the divisors are 1, 2, 3, 5, 6, 10, 15, 30. Okay. Therefore, we see that N3 is a divisor. It will be N3 will be among this list. The possibilities for N3 will be those who are congruent to 1 modulo 3, and we do have only two choices, 1 or 10. Similarly, for N5 we do have two choices, 1 or 6. Okay. Now I claim that one of N3 and N5 has to be 1, at least one of them has to be 1. Later on we will see both will be 1, but to begin with we will show at least one of them will be 1. So what does that mean? As I said that earlier, if NP is 1, that means you have a unique Sylow P subgroup. So what we will show now is, to put it in other words, it will have, so it's one of Sylow 3 or Sylow 5 subgroups, one of them must be normal. Okay. So how to do that? So we have to rule out the possibility when N3 is 10 and N5 is 6 simultaneously. So that's actually follows from a very common counting technique. So remember, two Sylow 3 subgroups, because any Sylow 3 subgroup here has order 3. So two Sylow 3 subgroups, two different Sylow 3 subgroups will always have trivial intersection. So thus, if you have 10 such subgroups, so you are in the intersection you are going to have only identity and nothing else. So in each Sylow 3 subgroup you have two elements of order 3. So from this you can immediately calculate that 10 into 2, 20 elements are there of order 3. Okay. Now similar argument goes for 5 as well. Here you can show 6 into 4, because in any subgroup of order 5 you have 4 elements of order 5. So you have 25 elements of order 5, but the group has order 30. So this certainly cannot happen. This is a very usual counting trick which we will be applying again and again. So that shows one of them must be normal. Okay. One of them must be normal. Let H and K be Sylow 3 and Sylow 5 subgroup. What we know then is one of them must be normal. So you can take any one, let us say H is normal. When H is normal, then just their product HK is going to be a subgroup of G, right? Because if one for two subgroups H and K, it will form a subgroup if one of them is normal. And then you see that what's the order of this subgroup? Since they have trivial intersection, this is going to have order 15. Hence, this is also normal in G. Okay. So our assumption is, let's say here we have assumed H is normal in G. Now this is quite clear that if G is in G, HK G inverse is simply HK, right? And K is contained in HK. So therefore, GK G inverse will be contained inside this. So GK, so all conjugates of K will be contained inside this 15 order subgroup. So these are all 5 Sylow subgroups of G, right. So you see that all Sylow 5 subgroups of G are now contained inside this subgroup of order 15. But 15 means 3 into 5, 3 does not divide 5 minus 1, 4. So therefore this is a cyclic group actually. So it cannot, so it will have a unique subgroup of order 5. So thus this shows all of them must be K, because K is already inside here, and any other conjugate of that being a subgroup of order 5 has to be equal to K. That means K also will be normal in G. So try to observe what we have done. Assuming H is normal, we prove that ultimately K will also be normal. The similar thing goes if you start with, if you assume K is normal, then from that you can show H is also normal. So that is, initially we proved one of them must be normal, and that in turn implies both of them will be normal. Okay? Fine. Okay, so this shows us what happens for when the group has order G. Next talk about groups. So like here I haven't completely classified the groups of order 30. This is just using Sylow's theorem. We are extracting this much of information. Again I will get back to groups of order 30 in some later lecture, where using this information we will be completely classifying that. So far this is what we obtain as by applying as an application of Sylow's theorems. So we are going to see that like what useful information we can extract using Sylow's theorem. So this is what we can do for groups of order 30. Now let us go for groups of order 12, the fourth application when G has order 12. So order 12 means what are the divisors? The divisors are 1, 2, just a minute, 1, 2, 3, 4, 6 and 12. Okay. So what are the possibilities? For N2 the possibilities are 1 or 3, for N3 the possibilities are 1 or 4, and for N2 and N3, because we only have these 2 primes. Now again as usual we can show that these 2 things cannot happen together, like N3, because this is 4 into 3, right. So that is easy to see, because if we have 4 subgroups of order 3, then we have 8 elements of order 3, and then we have at least one Sylow 4 subgroup. So thus that exhaust all elements in the group G, and hence there can be no other Sylow 2 subgroup, because already the counting is exhausted. So that is an immediate observation, that N2 equal to 3 and N3 equal to 4, these 2 things cannot happen together, therefore one of them must be normal. So that is what we have proved in a group of order 12, either Sylow 2 subgroup is normal or Sylow 3 subgroup is normal. Now let us consider the case when Sylow 3 subgroup is not normal. There we can see that in that case we can completely classify the group. So which is our ultimate goal, that we are developing all these machineries, theorems to classify finite groups. So now assume that let N3 is 4. Okay. So therefore H1, H2, H3, H4, let these are all Sylow 3 subgroups of G, and on this collection G acts by conjugation, right. In view of Sylow's second theorem, the action is transitive. This action is transitive. Therefore, what will happen? So, I mean, recall that when G acts on a set X, so the kernel of this action is the kernel of this homomorphism, and it's easy to see that the kernel of this homomorphism is nothing but the intersection of all stabilizers, because something is in the kernel if and only if it stabilizes every point in X, because that is giving the identity permutation there. So, therefore, the kernel of this, so for this action it leads us to the following homomorphism G to S4, let us call it phi. What about car phi? Car phi will be the kernel of the stabilizers of each of these subgroups. So, the stabilizer of Hi simply, that is exactly the normalizer, right, all right. Now, we can immediately, so for any Hi, it has orbit, its orbit has order 4, therefore, the stabilizer will have order 3, hence normalizer of Hi has order 3, and Hi is already contained inside normalizer Hi, that forces Hi to be equal to its normalizer. Therefore, this is nothing but intersection of all Hi's, and that is certainly going to be trivial because the orders are prime. Hence, we obtain that this map is a injective map. This map is an injective map, and yeah. So, therefore, G is isomorphic to phi G. Phi G has order 12. So, okay, and furthermore, so like all these 4, so each of these 4 subgroups have there are 2 elements of order 3. So, that images will be, so thus we will get 8 elements of order 3, okay, and in S4 elements of order 3 are 3 cycles. Therefore, there are 8 elements of 8 3 cycles in the phi G, and phi G has order 12, 3 cycles are always even permutations. So, it is immediate that phi G will be nothing but A4. Okay. So, that is what we have proved, that if for a group of order 12, so first we have proved that one of Sylow 2 subgroups or one of Sylow 2 subgroup or Sylow 3 subgroup, one of them must be unique, and if the Sylow 3 subgroup is not unique, then we do not have any choice other than G to be isomorphic to A4. Okay. So, thus in this case, this is a partial classification of groups of order 12. Okay. Now, let us move to other groups of other orders. Okay, next what we can prove we will go for is groups of order p square q, where p and q are distinct primes. So, again what are the divisors? 1, p, q, pq, p square q and p square. Okay. These are the possible divisors. We have 2 cases. If p is greater than q, then we see np has to be 1. There is no other choice from this list. If p is greater than q, then np has to be 1. Thus, we see that this for the, I mean the Sylow p subgroup is normal, and on the other case when p is less than q, this is where we have to be slightly more careful. Then What are the choices for NQ? What are the choices for NQ? NQ is simply like you have only two choices, 1 and p square, because all the other in the other factors q are present in the other divisors. So now this is somewhat interesting. If NQ is p square, if NQ is p square, then what can we say? If NQ is p square, then q divides p square, right? Q divides p square minus 1, because it has to be congruent to 1 modulo p. Q divides p square minus 1, so it's p minus 1 to p plus 1. Of course, q being a prime cannot divide p minus 1, p is a smaller prime. So that means q has to divide p plus 1, right? And again, p is a smaller prime, q is dividing p plus 1. So it forces q to be p plus 1, and in this case you do not have any other choice then. So p and p plus 1 both are prime, so p equal to 2 and q equal to 3. So thus the group will have order in this case 12. So what have we learnt? So first of all, so in what we have learnt is, if a group has order p square q, then either the Sylow p subgroup is normal or Sylow q subgroup has to be normal. So it will always have a normal Sylow subgroup. Okay. And furthermore, if p is the bigger prime, then NP has to be normal, and then the Sylow p subgroup has to be normal. That tells us the normal subgroups of groups of order p square q, which we will use later on for classifications. Now let us go for groups of order 60. So we prove the following, that if G is a group of order 60 whose Sylow 5 subgroup is not normal, that is there are several Sylow 5 subgroups. In fact, we can directly check from the divisors. What are the divisors here? Divisors are divisors are 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, 60. These are the divisors, and out of that you see only 6 is congruent to 1 modulo 1 and 6, these are congruent to 1 modulo 5. So n5 is greater than 1, it means n5 has to be 6. So what we are going to prove is, if G is a group of order 60 having whose number of Sylow 5 subgroups is 6, then G has to be simple. This is what we will prove now. So every group of order 60 which is having more than Sylow 5 subgroups has to be simple. Before we getting into the proof of this, let me deduce an immediate corollary from this. So do we know any subgroup of order 60? Of course, A5 is 1. So A5 has order 60, and then we can easily see that 1, 2, 3, 4, 5 and 1, 3, 2, 4, 5. These are two distinct 5 Sylow subgroups of A5. Therefore, from this it follows A5 is simple. So this is another proof of simplicity of A5. Of course, we have proved the simplicity of any general AN. For general other ANs, I mean when n is beyond that, certainly this proof doesn't work, this argument does not apply. But for n equal to 5, we do have a different proof. Okay. Yes, so let me now prove this. The proof of this is goes as follows. So all right, how do we prove? How do I think of proving this? So, if this is not simple, assume the contrary. And in fact, and let a maximal proper subgroup. Maximal means it is not properly contained in any other proper subgroup of G, maximal proper subgroup, maximal I think maximal normal subgroup, not proper would not be enough, maximal normal subgroup. So, maximal normal subgroup. So, again let me remind you what it means. It means that there is no other normal subgroup of G which is there is no other proper normal subgroup of G which is containing H properly. Okay. So, therefore, for order of H, what are the possibilities? So, of course, this goes, and as I said, this too goes. Now, let me directly compute G and G modulo H. So, if G is 2, if H is 2, then we have, so what are the possibilities? Let us do one by one. So, in one column let order of H, and then in another column let us put order of G mod H. So, if this is 2, then it will be 30, 3, it will be 20, let me again extend that, this table, 20, 4, it will be 15, 5, it will be 12, 5 it will be 12, 6 it will be 10. Let me also do it here. I think the better way is this. 6 it will be 10, then see after 6 what it comes is 10, 10 it will be 6, and 10 it will be 6, and yeah, and 15 it will be 4. Okay. So, and 3 possibilities are left, 12, 20, 30, these 3 possibilities we will deal with them later. So, the reason for only focusing into these first is that in either case if you see that since G is the maximal proper maximal normal subgroup, so G mod H has to be simple. Now, in each of these cases we see that these groups cannot be simple, as we have already observed. So, this cannot be simple, groups of order 20 is of 2 square into 5. So, it always has a normal Sylow subgroup. Similarly, this is going to be even cyclic, this is also normal group, this is also group of order 10. So, yeah, so this the group of order 10 that also has a normal subgroup, because 2 into 5 it forms in the it follows in the category of groups of order p times q. So, it always these have proper non-trivial proper normal subgroups. Similarly, for 6 and 4 is of course for 4. So, that shows that the only possibilities for H could be 12, 20 or 30. So, we will deal with them one by one. We will deal with them one by one. Case 1, H is 20 or 30. So, 5 divides, okay, so yeah, 5 divides H, okay. So, that means there is a H has a subgroup such that order of K will be 5, okay. So, we choose a Sylow 5 subgroup of H, and then for any G in G, so GK G inverse will be contained inside GH G inverse, which is of course H. So, you see that this K which is a Sylow 5 subgroup of H is also a Sylow 5 subgroup of G, and any other conjugate is also inside G. That means all Sylow 5 subgroups of G are inside H. All Sylow 5 subgroups of G are inside H. Okay, and that makes things interesting, because we have now inside H 6 Sylow 5 subgroups, and no two Sylow 5 subgroups will have non-trivial intersection. Therefore, thus you obtain 6 into 4, 24 elements of order 5 inside H. Inside H. (24 elements of order 5 inside H), and so this immediately rules out the possibility that order of H is 20. So this shows that this can be only 30, and okay. H all Sylow 5 subgroups of G. Now, so this is another problem. Then, if H is 30, the problem is all 5 Sylow subgroups of G are, so if H has order 30, then we see that this group of order 30 contains 6 Sylow 5 subgroups. So again, let me repeat that if this happens, then that means this group of order 30 contains 6 different Sylow 5 subgroups. Okay, and because all Sylow 5 subgroups of G are now Sylow 5 subgroups of H as well. And that cannot happen, because earlier we have proved that inside any group of order 30, the Sylow 5 subgroup has to be normal. So again, this is a contradiction. So in both the cases, we arrive at contradictions. Now we are left with only the case H is 12. With that, I will finish this lecture. Case 2, when H is 12. When H is 12. So when H is 12, inside H, of course, we have a normal subgroup, because in a group of order 12, either Sylow 3 subgroup is normal or Sylow 2 subgroup is normal. So there is a normal subgroup of order 3 or 4. Then once this is there, we can talk about G modulo K. So, well, it also follows that again in the previous logic, that now for every G in G, Gk G inverse is going to be contained inside H G inverse, which is H. Okay. So thus all these are going to be Sylow. So this is also a Sylow subgroup of So this is also going to be a Sylow, Gk G inverse is also a Sylow subgroup of Sylow 3 subgroup or Sylow 4 subgroup of H as well, and inside H is normal, so it has to be K. So thus K is also normal in G. Okay. So since let me repeat that, you just take the conjugates, you see that all of them have to be equal to K, because like H has a unique Sylow subgroup of that order. And now once that is there, the rest are quite immediate. So therefore G mod K will have order either, so if since K has order 3 or 4, G mod K will have order 20 or 15, order 15 or 20, okay, order 15 or 20. Then of course in this case Sylow 5, now let me come to this board. So so 5 is dividing that, right, 15 or 20 you can easily see from Sylow's theorem is Sylow 5 subgroup is normal. So, the Sylow 5 subgroup of G modulo k is normal, because for 15 we have already checked, for 20 it comes into the formula p square q, and since p and q are not equal to tu3, and then for the bigger prime, that it is 5 here, n5 will be 1. Okay. So, now taking pre-image in G, say n, what we obtain is in this what we obtain. So, the pre-image of the Sylow 5 subgroup inside G will be again normal. So, we obtain a normal subgroup of G. Okay, we obtain a normal subgroup of G whose order is simply 15 or 20, okay, depending upon the order of k is. And again, once we have a normal subgroup, of or normal subgroup whose order is divisible by 5, then this analysis goes on, and that yields at least 24 elements inside, at least 24 elements inside that normal subgroup, which cannot happen. So, once we obtain a normal subgroup whose order is divisible by 5, then this argument easily goes on, and that gives us the contradiction. Thus, we prove that if a group of order 60, if it has more than one Sylow 5 subgroup, then it has to be simple. Okay, so with that I will finish this lecture.